Hello everyone and welcome to Bye YAML, painless Kubernetes deployments with CDKs. My name is Cameron Tranthim-Fryer. Big thanks to our amazing sponsors. We could not have done today without you. We wish to acknowledge the traditional custodians of the land we are meeting on, the Whadjuk people. We wish to acknowledge and respect their continuing culture and the contribution they make to the life of this city and this region. So a little bit about me. Yes, I was a chartered accountant, but I'm lazy. I wanted to automate things. The profession had other ideas, so we had to part ways. Then I found out about this amazing job called DevOps Engineer, where I'd have the opportunity to automate all the things. So spreadsheets were my gateway drug, and now I'm hooked on AWS CDK with TypeScript. So I've been working with AWS for about 2 years now, and it is my preferred platform. During this time, I gained a deep understanding of CDK and many AWS services, and I've been able to use this knowledge to build complex applications with much less effort than what would have been required without CDK. I recently completed the AWS Associate Developer certification, and I highly recommend AWS certifications for anyone looking to turbocharge their career. I'm currently working in a DevOps engineer role at INX Software, where we build tools to help clients in high-risk industries, such as the mining industry, to manage their workforce and operations. And I'm working on a really interesting application modernization project. So let's just look at some of the terms in the talk today. So Kubernetes, or K8s, as it is often referred to, is an open source platform for managing containerized workloads. It traces its lineage back to Google's famous cluster management tool called Borg, which has been used to run Google services like Search and Gmail since the mid-2000s. Just a warning, this talk assumes some basic Kubernetes knowledge. So if you have not used Kubernetes before, you might get a bit lost about halfway through this talk. So CDK, or Cloud Development Kit, is a tool that allows us to model AWS resources using familiar programming languages. And it compiles down to YAML, mostly. CDK8s, or CDK8s, is a tool that allows us to manage our Kubernetes workloads using familiar programming languages. And it also compiles down to YAML. And the great thing about CDK8s is that the YAML produced can run anywhere. It can run on Azure, Google Cloud, or even your own self-hosted Kubernetes. And the example that we're going to look at later is my home automation project, which runs K3s on a Raspberry Pi 4. K3s is a lightweight Kubernetes distribution with a number of optimizations, such as using SQLite instead of etcd. And this makes it ideal for Kubernetes at the edge on cheap hardware. So let's have a look at the agenda today. First of all, we're going to take a look at YAML. We're going to consider both some good things and some not so good things about it. We'll look at some specific grievances that Kubernetes users have with YAML and how these can be overcome using popular programming languages with CDKs. We'll compare the release process for infrastructure as code to that for traditional software applications. And we'll consider why YAML makes sense as a release artifact. Finally, we have the serverless Kubernetes demo using AWS EKS and the serverless compute engine AWS Fargate. So I'd like to tell you a little bit about the idea for this talk. So earlier this year, I've been working closely with an AWS solutions architect to programmatically generate Docker Compose configuration using AWS Lambda. And this was to deploy a container stack to servers that were moving targets and had intermittent network connectivity. I've since taken this pattern and extended it to generate Kubernetes manifests for a home automation project. So I put my sales pitch together, submitted it, and then forgot about it. A few months passed, and then to my surprise, they contacted me and said, "You guys want to hear what I have to say about YAML?" So I took a look at what I'd submitted. Bye YAML? Sounds a bit creepy, doesn't it? Why? What's wrong with YAML? Firstly, what is YAML? YAML ain't markup language. Here's a small sample of YAML for those playing at home. YAML is a data serialization language designed to be human-friendly and to work well with modern programming languages for common everyday tasks. So it's kind of like JSON then, but using white space instead of curly braces, and with comments. Think of JSON as the lowest common denominator with a minimal feature set. YAML is a superset with additional features such as better readability for humans. Every JSON file is also a valid YAML file, and this simplifies adoption. So in this example here, one of YAML's additional features is references. And one of the downsides of this is that a malicious user using recursion could craft a YAML file which behaves like a zip bomb. And upon deserialization, will crash the Kube API server. And there's been several CVEs similar to this that have already been patched. So because of these extra features, YAML is not regarded as a pure data structure representation, as it has some additional features. If you want a pure data structure representation, I suggest taking a look at TOML, Tom's obvious markup language. You may have encountered this if you're interested in open source software, where it is often used for configuration files. So what's good about YAML then? When data is easy to view and understand, programming becomes a simpler task. It's a popular format for configuration files, log files, and declarative manifests such as Kubernetes and AWS CloudFormation. It provides a well-defined interface between humans and machines, and between machines and other machines. So a few years ago, BC, before COVID, we were visiting family in northern Thailand, and I was contacted by a colleague at work who notified me they were having some problems with the Kubernetes cluster. I simply asked him to run a few Kubernetes CLI commands with the flag --output YAML, and he was able to send me YAML that communicated to me the state of the Kubernetes cluster at that point in time. I was easily able to diagnose the error, change the YAML, and send it back to him. And once he loaded that YAML back into the system, it became operational again and resolved the problem. So why do I hear people complaining about YAML all the time then? Syntactic white space killed me. Any Python devs out there? Well, we know we can overcome this problem with better tooling, such as plugins for your IDE. I don't know a single engineer who enjoys writing YAML. Does anybody actually enjoy writing YAML? What we're talking about here is developer fatigue and frustration. I mean, how do you test YAML? How do you get assurance that when you deploy, it does what you want? Well, it's infrastructure as code, so that's good, right? Well, is it deployed from a pipeline or from a magic laptop with hidden dependencies? A YAML error, a YAML type error broke my deployment. So let's take a little bit of time to talk about YAML and type conversions. Given this section of YAML here, what would you expect the result to be upon deserialization? Australia, AU, New Zealand, NZ, Norway? False. We now have a mixed list, as no was interpreted as false. This is known as the Norway problem. YAML is very liberal when doing type conversions, and this leads to many errors. So let's look at some of the Kubernetes specific grievances with YAML. A lot of people complain that Kubernetes YAML is too verbose. And I mean, that's fair enough. It's designed for communication from machine to machine. And then you've got that whole drama with syncing labels across deployments, services, pods, etc. Another problem is delayed errors, like the Norway problem, which we spoke about in the previous slide. Often this is not detected until the pipeline fails, and this wastes everyone's time. People often complain that Kubernetes has too many features. So let's just compare that to Microsoft Word. Microsoft Word is a complex piece of software, but this complexity is hidden from novice users. With Kubernetes, all this complexity is in your face, and new users particularly find this daunting. The demo will show how CDK8s addresses these issues specifically. So one of the main advantages of YAML is that it is excellent for declaring the state of things. And that's why it's used for CloudFormation and Kubernetes manifests. It facilitates clearly defined interfaces between humans and machines, and between machines and other machines. Humans are happy to read it, but they don't like to write it. So similar to when we visit family in northern Thailand, all of the conversation is in the Thai language. I can understand about 1/3 to 1/2 of the words, and then I can figure out the rest. But when I try to respond, I really struggle to compose sentences. This is the problem humans have with YAML. It is easy to read and to make small updates, but try writing a Kubernetes manifest without any reference material handy. You're gonna have a bad time. We can overcome this problem by generating YAML programmatically with CDK for AWS CloudFormation and CDK8s for Kubernetes. So let's take a look at some of the advantages of generating YAML with popular programming languages. First of all, they're familiar to developers. So that means we can use conditional logic, loops, and other language features. We can use the testing tools we know and love. Both CDK8s and CDK support snapshot testing, and CDK supports fine-grained assertion testing. We can use the package managers we love, like using NPM instead of Helm. Libraries are easier to update, maintain, and share than templates. And we can use the IDEs and plugins and the linting and code analysis tools that we know. So dynamic versus static. Templates are static, whereas programming languages are dynamic. We can retrieve environment variables from AWS Systems Manager Parameter Store, or a container version from AWS ECR at compile time and save this into the manifest. Or we could read a file from the file system and save this into a config map to be mounted into a pod later. We can also use abstractions. This allows us to turn best practices into code libraries. And also the dry principle, don't repeat yourself. If you need to provision 10 of something, such as like a VPC with a database, maybe some EC2 instances, we can create a construct and then we can provision 10 of the construct. We can also test the construct. So what can we do if the YAML isn't right? Let's take a look at this example here. CDK allows us to embed YAML into CDK. So in this scenario here, this workplace has already invested heavily into the CloudFormation ecosystem, and they want to reuse some of their existing templates. So this user here has a template called mytemplate.yaml, and they can import that directly into CDK. There's also escape hatches. An escape hatch is an intentional leak in the abstraction layer. It allows users to escape the abstraction and reach out to a lower layer. In this example here, I found that AWS code build didn't do a full git clone by default, which is a problem if you want to use any git commands in your build. CloudFormation supported the feature, but it was not yet supported in CDK. Using this code here, I was able to override the YAML generated by the CDK to get the CloudFormation YAML right. CDK8s also has escape hatches. We also have the option of using CloudFormation custom resources. And a CloudFormation custom resource is a Lambda function that supports create, read, update, delete, and list operations. It's commonly used when a feature is supported in the AWS SDK, but not yet in CloudFormation. This is also very useful when using non-AWS resources. I often hear people say, I want to use Cloudflare DNS during the deployment. So that means I have to wrap the entire thing in Terraform, right? Well, you can write a CloudFormation custom resource that updates your DNS, and that is invoked by CDK. CDK also provides some very easy abstractions for packaging and deploying Lambda functions, which makes it very easy to write your own custom resources. I have one on my GitHub that I wrote for generating certificates to use with AWS IoT. Little fun fact for you guys, whilst researching this talk, I wondered to myself, what portion of CDK compiles down to YAML? And what portion uses custom resources? I don't have an exact answer for you, but I can report that of the total 192 CDK libraries, 10 use CloudFormation custom resources in some way, although YAML is still used predominantly. So what are the release artifacts in YAML when using Kubernetes manifests or AWS CloudFormation? It's not just infrastructure as code, it's also network as code, policy as code, configuration as code, even security as code, all of the things as code. And let's take a little look at the release process. It makes sense to use the same source, build, test, deploy, and monitor pattern that we use with our application code. So this little example here is in relation to my home automation project. So the source code is in Git. Merge to master triggers AWS code pipeline using version 2 of the GitHub source action. Build and test stages happen in AWS code build. Then a zip file containing the manifests and the app spec file are uploaded to S3, and a deployment is created. So all I had to do was install the AWS code deploy agent and K3s on my Raspberry Pi 4. And one of the things I love about K3s is that it has a watch folder. So any file found in the folder var lib rancher K3s server manifests will be automatically deployed to Kubernetes. So I configured my app spec file to instruct code deploy agent to copy the manifests into the K3s watch folder so that any point in time, the Kubernetes state reflects the source code in GitHub. This has the advantages of allowing me to view the entire configuration at any time by simply viewing the code repo and not needing to log into a server, to easily make changes to the configuration through PRs, or in my case, just committing to master. We can provision additional devices for friends and relatives. And of course, we can recover from failure, as Raspberry Pis are notoriously unreliable, and reinstallation is simply reinstall the operating system to the SD card, install K3s, which is a single bash command, and then install the AWS code deploy agent and run a deployment. So I also monitor this using AWS CloudWatch, which we have there at the bottom, extracting logs and metrics. Let's take a little look at containers on AWS. We have two control planes to choose from, which are really just container orchestrators. The first is ECS, or the Elastic Container Service. With ECS, you don't need to pay for the control plane, and it can be thought of similar to Docker Compose. Actually, last year, a feature was added to the Docker Compose CLI, allowing applications to be deployed to ECS by converting the Docker Compose configuration to CloudFormation transparently, and then deploying that to AWS. The second option is EKS, or Elastic Kubernetes Service. On top of the cost of your workloads, you will also pay for the control plane, which is US 10 cents per hour. And this works out at about $100 if you leave it deployed for an entire month. So if you try my demo, please make sure that you first set a billing alert so that you don't get a nasty surprise with your AWS bill. Both control planes have access to two options for deploying the workloads. The first is to deploy containers to managed EC2 instances as worker nodes. Or the second option is to use the serverless compute engine Fargate, where you don't have to worry about the underlying infrastructure and you pay only for the resources consumed, such as vCPU and memory. My experience of using Kubernetes is that I have often been disappointed with the poor utilization of the compute resources, and I've never been able to reach the level of application density and cost savings I was hoping for. And I always end up paying for idle capacity. There's also a significant maintenance burden that comes with maintaining infrastructure. There are workloads that are better suited to EC2 instances though, but for many use cases, the serverless option is the best. Okay. That was unusual. Where do we want to take it from? Sure. So, okay, so we'll go from control planes. So both control plane options have access to two options for deploying workloads. The first option is to deploy containers to managed EC2 instances as worker nodes. And the second option is to use the serverless compute engine AWS Fargate, where you don't have to worry about the underlying infrastructure and you pay only for what you use, which is the vCPU and memory usage. My experience of using Kubernetes is that I have often been disappointed with the poor utilization of the compute resources, and I've never been able to reach the level of application density and cost savings I was hoping for. And I always end up paying for idle capacity. Also, maintaining infrastructure results in a significant maintenance burden. There are some workloads that are better suited to EC2 workers. However, for many use cases, the serverless option is the best option, even though it is more expensive per unit of compute or memory resource. Okay, so let's have a look at the demo architecture today. So the first Git repo that we're going to be looking at today, which is the CDK one, this deploys our AWS control plane, our EKS control plane, and configures the control plane to use Fargate workers, which are the serverless ones I spoke about previously. So when we first deploy the cluster, we get 2 pods for core DNS, because you can't do much Kubernetes without DNS. And we also spin up the AWS load balancer controller. So the second code repo we're looking at today is the CDK8s repo, which generates our manifest for the Hello Kubernetes app. So when we use the Kubernetes CLI to deploy the Hello Kubernetes app, we deploy a deployment, which launches our pods. We deploy a service, which directs the traffic to the pod. And we deploy the ingress. And the ingress instructs the load balancer controller to spin up an AWS application load balancer. And the application load balancer receives incoming traffic and directs that to the Hello Kubernetes pod. So some advantages of using this architecture is that using the application load balancer, which is the newest and most advanced load balancer from AWS, we don't have to use an Nginx ingress. You may have used this before if you've used AWS with the classic load balancer, or if you've used load balancers with other cloud providers. So using Fargate provides better isolation, as each pod is scheduled on its own node and does not share the underlying kernel, CPU resources, memory resources, or elastic network interface with any other pod. Some of the advantages of this architecture, the disadvantages of this architecture, are that the ALB ingress controller spins up a separate ALB for each ingress, and this can get expensive. There's no support for stateful workloads that require persistent volumes when you use Fargate. So it's not so great for running databases, but there are other services for that, such as AWS RDS and Aurora. With Fargate, there's a 4 vCPU and 30 GB memory per pod hard limit, and daemon sets and privileged pods are not supported. There's no support for GPUs, and pods are not scheduled immediately. You'll have to wait around a minute for a pod to be scheduled on a Fargate node. Okay, demo time. Okay, so the first code repo that we're looking at is DDD demo CDK EKS Fargate, and I'll be providing this information at the end. So let me take you through what we're provisioning here with CDK. So the first step that we're using here is to create the cluster. And this is a fairly complex abstraction here. There's a lot going on. We create the cluster, we specify what Kubernetes version we're using, and then we also configure the default profile for the Fargate workers. So one advantage of using programming languages to generate this kind of configuration is that we can only enter values that we know are supported. So when it comes to Kubernetes version, I can select this here. I can let the autocomplete show me which versions are supported. And so I don't need to worry that I'm going to incorrectly configure this. We also have the option of using the language features. So when configuring the default profile here, it accepts an array of objects with a single property, which is namespace. Now, writing that out would be fairly verbose and quite annoying, but using the map feature of the JavaScript language, we can simply put all of the namespaces into an array, and the function will generate the structure for us. So this is a fairly complex abstraction here, an extremely powerful abstraction. But it's reassuring for me as an AWS customer that I can deploy such a complex architecture so simply. And if I'm a premium customer, I have the option of using AWS support as everything is supported from CDK through to CloudFormation to the resources actually deployed. I also have a wealth of local networking resources, such as the AWS Solutions Architects, that I can ask for help. And there's also online communities I can go to for help, such as the CDK project on GitHub if I want to raise an issue. So let's look at what we can do with this cluster object that we've created here. So we can access the properties of the cluster. So as you can see here, we can access the VPC ID and the VPC CIDR block. So if you wanted to add additional resources to the VPC, like a database or an EC2 instance or something like that, it's very easy to do. Or perhaps you wanted to add a security group to the VPC. There's also some helper methods here. So the first is to add node group capacity. So we're using Fargate here, but if we wanted to deploy a static EC2 worker node, we can do that with this function here. We also have the option of adding an auto-scaling group. And an auto-scaling group will scale up and down as capacity is required. And an interesting feature with the auto-scaling group is it has the option of using spot instances. Spot instances give AWS customers the opportunity to consume unused AWS compute capacity at very low prices. We also have the option to add manifests and Helm charts to the cluster. Now, I find deploying these types of resources to the cluster at the time that I deploy the cluster is useful mainly for things like loggers and controllers and sidecar injectors and that kind of thing. But I prefer to have a different deployment pattern for my workloads. And finally, this abstraction here gives us the option to actually deploy CDK8s charts directly to the cluster. So in this example today, the CDK8s code is in a separate repo because we're going to be using it to generate the YAML, and then we're going to apply that YAML to the cluster using the Kubernetes CLI. But if you wanted to have it all in the one repo and have everything deployed in one go, that's easy to do using this abstraction. So next we have another abstraction here which deploys the ALB controller that I spoke about previously. And this is a fairly complex abstraction as configuration is required both at the AWS control plane level for things like creating IAM roles and also at the Kubernetes control plane level to deploy the controller. But this abstraction handles that low level complexity for you. So let's look at tests. If we click the test file here, we see that there's two types of tests. So here we have the snapshot test. And snapshot tests are really useful for preventing regression during refactoring. We can refactor our code, and then by running the test, we find out whether that code generates the same YAML. And with CDK, we also have the option of testing fine-grained assertions. And that's this test here. where we're saying we expect that the stack is not going to have an S3 bucket. Now we can actually test a lot more complex assertions than that, so we can test the properties of the S3 bucket, but this is just a basic example here. So fine-grained assertion testings are really useful when you have a well-written spec, as it is very easy to translate this into a test. And then it is easy to write the CDK that passes the test. These tests provide a reference point for non-technical users wanting to understand how the system works, and for developers working on the project for the first time. Knowing that what you are deploying is the right thing before commencing the deployment will save you a lot of time and save your employer money by not deploying infrastructure that does not deliver any business value. So once we've written our CDK here, the next step would be to run yarn deploy, and it takes about 25 minutes to spin up this stack. And when that is complete, it prints out some properties of the stack, and that includes an AWS CLI command that you can run to import the access credentials for the stack, which will then allow you to access the stack remotely. And we'll come back to that in the demo. So let's take a look at the second code repo, which is the CDK8s repo. So we're going to start on the file called CDK8s.yaml. This is how we configure CDK8s. This is a very simple example here, and you can see that we're configuring CDK8s to use version 1.20 of CDK. So once we've done this, we run the command yarn import, and CDK8s will create TypeScript classes for all Kubernetes objects, for instance, deployments, services, etc. Now, if you have custom resource definitions, you can also import them here too. And CDK8s will create TypeScript classes for your custom resource definitions. So let's look at the CDK8s code itself. So a common Kubernetes application will have the deployment, which deploys your pods. It'll have a service, which directs traffic to the pods. And you'll have an ingress, which allows external users to access the resource. So let's look at those configurations here. First of all, we have the service. And one really great thing about CDK8s is we can hover over the service here, and we can see that this object here defines an API object of this type here. So one of the frustrations of Kubernetes is getting all this stuff correct. So because we're using CDK8s and we told it that we're using version 1.20 of Kubernetes, it ensures that we get all these annotations right and we don't have to worry about configuring them manually. So with the service, we define it of type node port. So if you've used Kubernetes elsewhere, you might be used to the load balancer type of service. This is what I've commonly seen before. And it took a little while for me to understand here that because we're using the application load balancer, we actually need to open the port on the node or on the Fargate pod itself, because the application load balancer is going to direct the traffic directly to the pod. So after we've created the service, we could create the ingress. And as you can see, the ingress has these three annotations here. And these annotations configure the ingress to communicate with the load balancer controller so that the load balancer knows it needs to spin up a load balancer. The actual configuration here is, there's a lot of boilerplate. You can see we're just using the root, and we're just mapping that service, the service that we defined up here. Next, we have our kube deployment. And so we specify here that we want 2 pods, and we want to run the Docker Hub image called Hello Kubernetes version 1.9. We configure the ports, and we're passing in a message here as an environment variable. One thing to notice here is that a lot of the complexity is hidden. So if we wanted to add additional configuration for the container, we can simply add a new line, and then we can use autocomplete to see all of the properties that are supported by that container. So I want to draw your attention to the top of this page here, where we define the label. So one of the biggest grievances that Kubernetes users have is keeping their labels in sync. I know I've lost countless hours on this task. But using CDK8s, we simply define the label once, and then we reference it where we want to use it. So we define that as the selector for the service, and then again on the kube deployment, both at the selector section and also in the template section. So you may notice here that there's still quite a bit of boilerplate here. So you might find that you're constantly writing the same charts over and over again. Maybe you just want to change one property, such as the container name. CDK8s supports these kinds of abstractions, and they're called constructs. So if you were in that situation, you could simply publish this as a construct, and then you've got your regression testing on that as well, so you know that it hasn't changed. And then you can just consume that construct as many times as you want. So after we've written our code here, we would run yarn build, and that would build our code. And let's have a look at what that looks like. So this is the YAML that is output here. As you can see, we have our service of type node port. We have our ingress with our annotations. And we have our deployment, which is going to run 2 containers of the Hello Kubernetes app. So let's deploy this YAML to the cluster now and see how it works. Okay, so that'll be a stop. Go back to separate display.
Are you actually going to be deploying?
This is the video.
Gotcha.
Oh, so I'll just be talking. Okay. So we've run the command to configure, oh, sorry, is this recording again? Okay. Okay, so here we go. We've run the command to configure the Kubernetes CLI. But today I'm going to be using this fantastic desktop app called Lens. If you haven't heard of it, I suggest you check it out. It gives you all of, if not most of, the functionality of the Kubernetes CLI, but in a desktop app that's much easier to understand. So let's connect to our cluster. Here we go, we're connected. So let's look at nodes. Oh, let's look at workloads first. So we change the namespace to show all namespaces. And we can see we have 4 pods. So we've got the 2 DNS pods and the 2 pods for the load balancer controller. And then if we look at the nodes, we can see that Fargate has provisioned a separate worker node for each pod. And we can click those and we can see that each node has 2 vCPUs and 4 gigabytes of memory. So let's add a demo namespace. We'll just do that manually using the GUI. And now we're going to deploy our manifests into that namespace. Okay, so our resources have been created. So if we go to pods, we see that there are 2 pods that are currently in a pending state. If we go to nodes, we've got 4 nodes. And another 2 have just popped up. Let's take a look at our pods. Still pending. Here we go. Both pods are successfully running now. So now if we go to the network section in Lens, go to Ingress, we can see the ingress that the load balancer controller has created for us. So we can copy the host name of the load balancer controller, paste that into Safari, we can see our application. Now if we hit refresh, you'll see that the pod name is changing here. And that's because we've got two replicas and the load balancer is directing the traffic between the two different replicas. So in this demo, I showed you how much easier it is to spin up a Kubernetes cluster on AWS with CDK and to deploy workloads with CDK8s, especially when compared to writing CloudFormation and Kubernetes YAML manually. This process addresses the problems with YAML that we learned about earlier in the talk. The demo also gives you an understanding of how Kubernetes works on AWS in conjunction with the serverless compute engine Fargate and the application load balancer. So if you are using AWS but not CDK, or if you are using Kubernetes with YAML manifests, I hope you will go home and deploy my code to try it for yourself. So here are the links to the code repos. I'd like to say a big thanks to all the volunteers for making today possible.